I got a couple of questions during the coffee break, and it's a good time to answer those questions. And start with what on earth is A and B? So that was the first question. Um, as you have noticed that center of resistance is depicted in a purple circle. Okay, this is center of resistance, and the center of rotation is depicted in blue dots. Either in the program or in the book, it's consistent. Okay? The blue dot is the center of rotation, and the single force is depicted in red arrows. Okay. Now, let's suppose force is applied somewhere here at the crown. Okay, then the tooth is going to tip. So it is going to rotate around somewhere here. So this is before tooth movement, and this is after the tooth movement. As you can see, the tooth has moved around here, which is the center of rotation. Okay. Now, if you measure the distance from center of resistance to the single force, this is called A. And if you measure the distance between the center of resistance and the center of rotation, that is called B. Okay? It's simple as that. Very simple. And very complicated is something like this. The product of A and B, A multiplied by B, is constant. That's the law in orthodontics, which Dr. Burson invented. Okay? So that's this journal says. And this is the figure 1 in his journal, okay? And it was written back in 1969, quite a long time ago, right? And this is the figure 1. And it's very difficult to understand for the first glance, so I'll replace it with contemporary formula. Okay, so you look at this here, and it says, in his journal, it says, moment to force ratio equals 0.068 times h squared divided by y. What is this? This is Burston's formula, and I'll explain about this. So, if I add up, this is the explanation of each term. So, the moment to force ratio he mentioned about is the distance between the he called it centroid, not the but in contemporary terms, centroid is center of resistance. Okay, so this is center of resistance, and MF ratio is the distance between center of resistance and the single force over here. In contemporary term that I showed you this is A. The distance between center of resistance and single force. Okay, so this is A. And this is B. He depicted in Y. Okay, this is Y is B. This is they are the same. Okay, and this is H, which is the length of the root. Okay, so I was not about to tell you the numbers, but it's very interesting here. If you call Y is over here at the denominator, so we can multiply Y at each term. So moment force ratio times Y equals 0.068 h squared, right? So these are A and B. So A times B is something like this. And as you can see, this is a number. And once there's a tooth, the H is the length of the root, so is constant for a given tooth. So his whole number here will be constant value. Okay, so it goes like this, and this, and finally we have an s squared. That means this is constant. A times B is constant for given tooth. Okay? So this is what A and B. So if A times B is constant, if we know the B, A is automatically determined. If we know A, B is automatically determined because s squared is already known. So this is what A and B means, okay? So, if we apply to this center rotation calculator, force is applied it here, and center of resistance is moving from here to there. So the distance between the force and the center of resistance, the distance between here, this is A, okay? And the distance between center of resistance and the center of rotation here, this distance is B. So here it says B is 12 millimeter, and A is about 3 millimeters. So here's 3 millimeter, and this is 12 millimeter. That is what A and B is, because the time, the product of the A and B is constant. Okay? So that's what A and B is. And now we'll start to explain about the left panel over here that I skipped. So I would like to explain about it more about it. So let's hide the image here. So go to View menu, and I can do Images checked. So I uncheck it, so everything will disappear. And if I click at the center of the protractor over here, see here? Then everything goes back to the original position. Now, you can see that there are File menu, and View menu, and Tool menu, and Help. And what File menu does is, if you click the File menu, there are many drop-down menus saying that open the image. If you have an X-ray in your computer, you can open up the image using that open image using Control-O, which is a shortcut. Or as we did before, if you might not have a image in your computer, you might see the image in my presentation and you want to analyze, you take a photo of it and then move it to your computer and you can open it, or you can just take a photo and you use the copy into clipboard, as I showed you, by using Control-Shift-S, and you can import the clipboard image directly into this canvas here. That's import image from clipboard, which is Control-Shift-I. And once you analyze everything, once again, you can save it to your computer using an export JSON file here. Later, you can import the JSON file using Control-Alt-I. Okay? So let's suppose I already made some, and this time I'll show you about the next question would be, what on earth is equivalent force system? And force is applying, and when do you apply couple and when do you apply the force? I will explain about it tomorrow in detail, but I'll give you a brief. I'll explain about the big picture so that it will be easier for tomorrow course. So let's suppose I import something. So rather than importing, I'll explain about the left panel here. This rectangle over here is the alveolar bone. So if you can see here, there is the root length is about 13 millimeter. I quote that number from the textbook of morphology. So average length of the central incisor will be 13 millimeter. So I put the 13 millimeter as a default. But let's suppose we are analyzing cuspid or molar or some other teeth with a different root length. So then I can change the length of the root here. So let's suppose we are analyzing the cuspid. For average length of the average root length of the cuspid, let's suppose it's 20 millimeter. Okay? So I increase this number from 13 to 20. So it has been increased to 20. So you can see that the length has not been increased actually. Instead of that, the scale bar is changing here. So as I decrease the number, look at the scale bar here. So if I decrease the number, scale bar increase. You see? Scale bar is increasing if I shorten the length. If I increase the length, the scale bar decreased. So the actual length does not change, but relative length changes by changing the scale bar. That's what root length is. So let's put it back to reset. So it's 13 millimeter. It's a good point to start with. Now, for adult patient, there might be a root resorption. The alveolar bone resorption, right? So for this, in this case, default value is very healthy periodontal condition. Let's suppose it is an adult patient and alveolar bone has been lost a little bit, like 1 or 2 or 3, 4 millimeter. I increase the alveolar bone loss here, which is a B value here, so I can increase it using an arrow key or scroll bar or whatever. As I increase the alveolar bone loss, you can see alveolar bone is going up, right? And also the center of resistance is moving up at the same time as you increase or decrease the alveolar bone loss. So let's suppose there's no alveolar bone loss, okay? Now, this is a location. Now, next item is a location of the center of resistance. As a default value, it is about 34% measured from alveolar crest. So it depends on the shape of the root, but averagely it's about 30 to 40%. So normally you don't have to change, but if you want to change, you can change it here. So if you move this slide bar up and down, so that you can see the center of resistance is moving from up and down here. So I will not move it normally. So I'll just use the average value, which is about 0.34% of measured from the alveolar crest. Okay. Now, last question is, one of the doctor asked me, that's the constant value S squared. Constant value depends on the shape and the shape of the root. Let's suppose, is it still valid? It's valid for incisors, but what if I want to analyze the movement of the molar? Suppose I want to expand the maxilla and I want to move the molar in control tipping. Where should I put the force? Okay, that's a very good question. In that case, you can adjust the length and the bone loss as depicted here, and you use the number here. This is sigma square value that I explained it. I was not about to explain about this because it makes you very confused. However, as I get the question, I'll answer. If you are using a very fat tooth, like molar, or whole anterior segment is connected with a rigid wire, the length is the same, but the width becomes wider, right? In that case, sigma square increase a little bit. The average value of sigma square, the range of sigma square is, you can move it from here, so that it is from, if it's 0.261, that's sigma square, that's the value of the square root of the sigma, okay? So you can see that the gamma value over here is 0.068, which is exactly the same as Dr. Burston's formula, right? So Dr. Burston's formula was developed under two-dimensional model, and in three-dimensional model, it increased up to 0.466, okay? So it might be difficult to understand, but if you are analyzing the very fat tooth, you should increase that value. And if you are analyzing very thin tooth, you should decrease it. But averagely, you can just leave it in a default value, averagely. So it's a little bit complicated to understand. If you have time, it'll take whole day to explain about the gamma square value. Okay, so this is the one that you change when you're using a different shape of the root. But for now, just forget about it and just leave it as a default value, okay? So this is what this left panel is. Now, on your right panel, which is the canvas, which image is drawn. So once you import the image, thing like this, I will import the image that I saved before. Let's import this. On the file menu, I have explained open, import, import JSON, and export, right? And on the view menu, there are many options here. As you can see, these are the shortcut. And if you unclick this image here by Control I, then it's going to hide the image. So if you click it, or you to put Control I, it's going to show you. And sometimes it is too dark, so that you cannot see the numbers here. So in that case, you can change the theme of this program by Control M, which is here, down there. There's a dark mode is clicked, so it is running in dark mode. So if you click Control M, it's going to be a light mode. So if it's too bright, if you are working in the airplane or working in the hotel room in the midnight, it's too bright, so you can make, I prefer dark mode, so I prefer this, okay? And if this X-ray is too dark, so that you cannot see the numbers here, then you can do these options here, controls the image. You can hide or show the image, or you can make it negative by Control N, like this. You can see the negative image. And if this is black and white, but let's suppose you are importing a very colorful X-ray or whatever image is, you can change it to grayscale. It doesn't change because it's already grayscale. And if it is not enough, you can make it transparent. So image becomes transparent, so that it's much easier to see the numbers here, okay? And these are the controls here. So every shortcut is color-coded here, right here, on the right panel, the canvas. So let's put it back to default. So Control T, Control negative, so it's original image. And in this case, the alveolar bone is not anymore relevant, so I want to hide the alveolar bone. So just click this yellow alveolar bone. If you click it, alveolar bone will be hidden. And let's suppose you want to. I don't want to see the force arrow. I just want to see the line of action. So you can click the red one. The color corresponds to the actual color. So if you click the red button over here, the force will be hidden. And also the line of action is in blue color. Okay. I'll hide the image. Okay. And if you click the green over here, the bisector lines will be hidden. If you put purple here, the long axis of the tooth will be hidden. The gray color is the numbers. If you don't want to see the numbers, you can click here. And if you don't want to see anything else, handler, you can click the black button over here. It hides everything. And sometimes, if you don't want to see the tooth, it's superimposed and make you confused. You can do Control 1 and 2. If you press Control 1 and 2, tooth will be hidden. Okay? So these are the shortcut, the view menu. So if you click the lower right corner, everything will be reappeared. Now you can move into any place you want. And I wonder if you are controlling the drones. Somebody raise your hand if you have a drone. No. If you're having a drone, I don't have a drone, but if you're controlling the drone and it goes away out of your sight, you're losing your drone, right? So in that emergency, there is a home button. If you press the home button, no matter where the drone is, it comes back to your takeoff place. So this is a home button. So let's suppose this tooth is moved out of the screen. You can move it back. So in that case, you can click here. center of the protractor here, it's going to bring every tooth into home position. No matter where you have moved, you start from the beginning. Now let's now as a so I am quite familiar with analog rather than digital. So I prefer use a protractor rather than computer. So in this case, I can move the protractor, and let's suppose I want to see the angle of this line of action. So I can move this protractor here, okay? And using a scroll key, you can increase or decrease the protractor like this. So you can see that this line of action is about 40 degree, right? So as you can see the number here, it says force direction is 39.4 degree. So you can confirm it using an analog protractor if you want to move it. And once again, click the center of it. It's going to bring everything at home like this. So this is how you use. Now it's time to explain about the numbers here. So number here, first one is B. Value of B, that is a distance from center of resistance to center of rotation, right? So in this case, tooth has not been moved at all, so there's no numbers here, not available. Let's suppose it has been moved from here to there as a translation. It has been translated. So as this is translation, the bisector does not meet each other. That means B is at infinity. So you can see that B is at infinity. And how much is the A? The center resistance and the force are coinciding each other. That means A is 0, right? So it says A is 0. And the force direction over here says it's almost vertical. Okay? And the moment to force ratio required is about 10. I will explain about the moment to force ratio briefly after this. So I have explained everything about it. And sometimes, time to time, if I upgrade the program, when you start up the program, it says new version is available. Okay? In that case, how to download a new one? You can click this multi-tool here on the lower left corner. If you click this icon over here, it opens up the site, and you can go down and click here to download the new program. So in this case, you can see the old Excel version here. And this is very old Mac version. It's tricky, so some machine works, some machine doesn't. So it's just experimental. And here is the BTK window version. If you click here, you can go into window version, and it gives you a sample file. You can download the sample file over here. And here's each BTK program to download. Okay. Now it's time to explain about the center equivalency and moment to force ratio. So I have explained about this left channel here. And if I translate the teeth, the moment force ratio would be about 10. I will explain it if you are not familiar with this. Let's suppose in translation, we cannot directly apply the force over here because that is inside of the root, and it is very difficult to apply directly the force up there, right? So instead of applying here, force is applied here, and counterclockwise moment is applied. the ratio between the force and the moment is about 10. So this is what it says, moment to force ratio. If the moment is 1000 gram millimeter and force is 100 gram, it is exactly same as force applied over here. Okay, so let me explain about that in detail. So as we get the big picture, you see what it is. This is a schematic drawing of the moment to force ratio, and depending on the moment to force ratio, the center of rotation changes. And I'll explain about this. As I've showed you before in the morning, that there's a descriptive term of type of tooth movement, saying that if the center of rotation is near the center of resistance, somewhere here, rotation around here, it's called uncontrolled tipping. Okay. And if the tooth rotates about the apex, that's controlled tipping. And if it translates, there's the central rotation at the infinity, up and down. And if the root is moving, rotating around the incisal edge or the bracket, that is called the root movement. And this force indicates the location of the force that we calculated using the center rotation calculator. So how much is the moment to force ratio? It's like this. And I'll explain about this. Let's see. Let's suppose force is applied at the center of resistance. It's going to translate. And my question is, where is the center of rotation? I said it is infinity. So why is it infinity? Suppose tooth is very small, okay? Way up there, or way down there, whatever it is. And center of rotation is in here. It is in blue dot. And it rotates around here. And force is applied at the center of resistance, and this tooth rotates around here. So let's suppose it has been rotated a little bit, like 1 degree. It has been rotated around center of rotation here, very far away. Okay? And let's take a look at here. I'll close it up. If you take a closer look, it has been rotated somewhere around here, but it looks like it has been translated, right? So that means if the force is applied to center resistance, it translates. In other words, center rotation is very far away. That's what it says. And now, or let's suppose center of rotation is far away up there. It's the same. It has been rotated 1 degree. If you take a closer look at it, do you see it has been rotated or it has been translated? It's very difficult to distinguish, right? So if center of rotation is very far away from the center of resistance, that means it has been translated. Either up or down. Now, so if you're applying the force at the center of resistance, that means if A is 0, B goes infinite. Because A times B should be constant. So 0 times infinite, what is it? Mathematically, it's indeterminate. There's no answer, right? Or I could say too many answers. Now, let's move the tooth a little bit upward from the center of resistance. We can do it using our smartphone. You can put your smartphone over the table or any other objects and try to translate this. then you have to put the force at the center of resistance, right? Okay. Now, if you put the force a little bit, just a little bit above the center of resistance like this, okay? So how much is the A? A is like this, or 2 or 3 millimeter, okay? Then, the center of rotation goes from infinity to here. So it's going to rotate somewhere around here. It tips a little bit. If the force is applied a little bit above the center of resistance on your smartphone, you can try it. And if it moves a little bit more upwards, let's say force is applied at the cervix here. Then, how much is this? About 5 to 6 millimeter, let's say, averagely. Then center of rotation moves from here to there. So this is A, this is B, and A times B should be constant. Okay? So this is called control tipping. So when tooth is undergoing control tipping, the force is away from the bracket about 5 to 7 millimeter. It's called control tipping. And let's suppose I move the force a little bit more upward at the center of the crown. This is what happens if we put the spring at the bracket without any brackets. No moments, only single force is applying at the crown. Something like using a finger spring and removable appliance, or retracting anterior teeth using a round wire. There is no moment, only force is applied at the crown. Then, center of rotation moves here. It goes up because A is getting greater, so B should be lesser, right? So A times B is always constant. So it goes like this. Crown goes this way, apex goes the other side. So this is called uncontrolled tipping, and force is acting here without any moment. So the moment to force ratio, there's no moment is 0, so moment to force ratio is 0. If moment to force ratio of 0 is applied at the bracket, tooth is all going to undergo uncontrolled tipping like this. So what is the difference between uncontrolled tipping and controlled tipping? Both are tipping, but the important thing is if the force is applied at the cervix like this, all points are moving in the same direction as force is applied. Okay? But in uncontrolled tipping, there is a part of the tooth moving in opposite direction. So even if you are putting a force to the right side, crown moves to the right side, however the apex moves to the other side. So it goes round tripping, unwanted movement, mostly. So, and also, the stress is very high here. So whenever possible, you should avoid uncontrolled tipping. Okay? So if the force is applied over here, we cannot apply the force at the empty space. So let's suppose we put the extension wire here, which is infinitely rigid, and if you apply the force over here, as A is increasing, B should be approaching center of resistance. It's going to be smaller, right? So it goes like this. That means the lady, he asked me during the coffee break that force is away, like MF ratio is about 30 or 40 millimeter. How do you do that? So if the A is very large, that means there's no force. You better apply the couple instead of the force. So if the B is very small, that means tooth is rotating around the center of resistance. Clinically, they are saying, so instead of putting a force away, quite long distance away from the center of resistance, very difficult, right? Applying the force about 30 to 40 millimeter away from the center of resistance is practically impossible, right? So in that case, rather than applying the force, you can apply the couple instead. So if the force is away from the center of resistance, in other words, if A is very large, it goes uncontrolled tipping, and couple is applied is better. Applying couple is better. Like this. If this is very large, you can see that B becomes very small because A is very large. A times B is constant, right? So then what is moment to force ratio then? Now let's try to understand what moment to force ratio equivalent force system is. Once again, put your smartphone over your table and put the force at the center of resistance so that it translates. Okay, that's not difficult, it's very easy. But clinically, you cannot put the force over here. The only way you let's suppose you put the bracket here, this is at the crown, and the only place that you can apply force is at the bracket here. And you want to translate. How would you translate the tooth? Does it translate by by one finger? No way you can't. The only way is you use two fingers. Okay? So put two fingers over here. Okay? I'll show you here. Okay? So over here, and rather than applying the force here, put two fingers here and rotate it counterclockwise and move it to the left side. Like this. So that's moment to force ratio. If you put the moment using two fingers, you can translate, and that's the equivalent force. So the single force at the crown and applying moment at the force at the same time using a bracket is an equivalent force system. So here you can see that this is the center of resistance. This is a book or a smartphone. You put the force here, you can translate. Okay? But once again, you cannot put the force over here. The only way is to put the force at the bracket here, somewhere. So move the force down there. And if you apply the force, it's going to tip. It's going to rotate. That's not what you want. We want to translate. So rather than putting a single force, we apply, how can we do this? Let's take a look at this video. So if I apply the force at the center of resistance, I can translate, as we did, right? But if I use the two fingers rather than one, I can twist it counterclockwise and put the force at the same time. Like this. So upper finger should be put more force than the lower finger in the opposite direction. Okay? So if you put it this way, there are double force here. So these two are coupled. These are the force. And the ratio between the moment and the force is the moment to force ratio at the bracket. So this is it. This is the moment that you apply, the yellow one. And this is the force that you apply. So if you apply the force and the moment at the same time, now you can translate. Like this. Right? You can do it your smartphone over the table. So that's how you translate the T. That's what bracket and rectangular wire is doing. And we are going to practice how to use that moment to force ratio tomorrow. So it's just that I hate to show you the numbers and the formula, but it's simple so that we can understand. It's very basic. Okay. So let's suppose you're applying 100 gram here. 100 gram. Okay. Now what we want to do is apply the force in the moment over here, which is the same as this, and we don't know what it is. And so I put the variable like F and M in arbitrary direction, in right direction and clockwise as a positive. And we measure this distance between these two forces. It's a 10 millimeter, let's say, averagely in size. And for the red one and the yellow one should be same. There are two conditions to meet. And first is sum of all force should be the same. The sum of all force in the red system is minus 100 because I said right and clockwise, right direction and clockwise direction is defined as positive. So this is minus. So minus 10 would be this force and this force should be the same. Okay, and the moment on the red force system calculated from the point over here, so it's 5 millimeter each. So the red one gives you the counterclockwise direction of 500. And the yellow one gives you the minus 5 times F plus M. So we solve these equations. So we can say that moment and force is 100 and moment is minus 1000. So this is what moment to force ratio is. If you divided this moment by force, it becomes 10, right? So that 10 means single force. 10 is not. If you divided 1000 gram millimeter by 100 gram, the gram is eliminated, so millimeter left. So moment to force ratio is nothing but the millimeter distance. What is the moment to force ratio? It's the single location of the single force from the bracket. How many millimeters away from the bracket? That's the moment to force ratio. Simply, it's simple as that. So if you apply moment to force ratio about 10, that means you are applying the force 10 millimeter away from the bracket upwards. Okay. So if you apply this moment to force ratio about 7, that is 700 gram millimeter and 100 gram, its moment to force ratio is about 7. That means the distance from bracket to the force is about 7 millimeter. So in this case, the force is applied here without any moment. That means moment to force ratio is 0. If you apply the force over here, it's going to rotate around here because A times B is always constant. And if the force is applied here, it's going to translate. If the force is applied above the center of resistance, now it's going to move the roots instead. And once again, applying the force here and applying a force like this is very difficult. So instead of using a single force, we use the equivalent force system. That is depicted in yellow color. So you can see that the moment to force ratio increases as it goes to the right side. Okay? So how much are they? The yellow and red are the same, exactly same. In other words, that's called equivalent force system. And how much is the ratio? It's 0, it's 5 to 7, it's 10, and it's 12. Just memorize it for now. Understand it later, okay? Just memorize it. 0, 5 to 7, 10, and 12. That's uncontrolled tipping, control tipping, translation, and root movement, okay? And let's see it is true using the central rotation calculator. So open up the calculator again. Oh, one more slide I would like to show you. I'm going to show it to you tomorrow, but here it is what the equivalent force system is clinically here. As we apply the force like this, on the left side, the force is applied at the center of resistance so that the left tooth is going to translate. On the right side, the force is applied a little bit below the alveolar crest, right? So it's going to control tipping. So central rotation is somewhere here. So you can see this translates, and this one is control tipping, control tipping. And clinically, applying force like this is very difficult, okay? So instead of using a single force, you use the T loop, which we will make it tomorrow. So force is applied at the bracket, not at the middle of the loop like this. But as you can see, this and this looks the same. Left one translates, and the right one is undergo control tipping. So what happens is, the red point is the point of force application, and clinically it's not possible. So this is what it does. So it goes up like this, and there is a moment to force ratio. So it goes translation, and it goes control tipping. So my question is, how much is the ratio between moment and the force on the left side? We memorized it just before. The left one translates. So how much is the moment to force ratio? 10, correct. How much is the moment to force ratio on the right side? It undergoes control tipping. 5 to 7, okay? So let's confirm it, if it is correct, using a central rotation calculator. So let's close this, and open up the calculator again, and bring everything to home, clicking the home button over here. Now, we are translating to the left side. So you can use this button over here, use Shift key, and press left button on the blue one. So we can translate. So I have translated it to left side to 7 millimeter. It says how many millimeter has been translated in X direction. And in Y direction, it has not translated at all. And the delta theta means the amount of rotation. It says 0 degrees, so it has been translated. If you see this degree 0. Now, the bracket is over here, and you can see that how much is the moment to force ratio of translation? 10, right? So take a look at the right side over here. How much moment to force ratio is it? So it says 10. That means if you apply the moment to force ratio about 10, it's going to translate. And my question is, the moment to force ratio is distance between center resistance and the bracket, and it depends on the position where you put the bracket, right? So let's suppose you put the bracket a little bit upper to the cervix. Move it upside, move it to up, like this. And you put the bracket not at the center of the crown, I put the bracket more apically. Then the moment to force ratio becomes 7. So the number that we memorize is for average value. It depends on where you put the bracket, okay? Let's suppose you put the bracket at the incisal edge, like this. Then the moment to force ratio is the distance from the force and the bracket, so it increases up to 12. So we memorize that 12 is a root movement, but why does it translate? That's because you put the bracket too much occlusively. So the number that we memorize is just for average value. Okay? Now let's put back to home position. Now we'll do control tipping. Okay? So I moved it a little bit left to left side. Okay? And rotate it so that APCs meet each other. Now move it up. So now it is under control tipping, right? So how much is the moment to force ratio? It says 5.3, right? So we memorize that 5 to 7 is control tipping, right? So it's the moment to force ratio you have to apply here. Once again, the moment to force value here depends on the position where you put the brackets. Now let's do root movement. So the rotation center would be at the incisal edge. So as I translate, it goes down. So I rotate the tooth around the incisal edge, and how much is the moment to force ratio? It's about 12.5. So it has been confirmed from the calculator that 5 to 7 is control tipping. 0 is, let's simulate 0. What is 0? Only the force. Force is applied over here, right? So I'll translate that a little bit. And rotate it until the force is at the bracket. Okay, now force is applied at the bracket, right? And where's the center of rotation? It's somewhere here. The crown moves to the left side, and apex is moving in the opposite direction, right? It's under uncontrolled tipping. Now, how much is the moment to force ratio? It's minus 0.25, almost 0, right? So the center rotation calculator confirms that the number that we memorized, 0 is uncontrolled tipping. Once again, 5 to 7 is control tipping, 10 is translation, and 12 is root movement. You have to memorize it because we are going to use it tomorrow. So I will not explain it tomorrow in detail, okay? Now let's go back to the question that I asked at the beginning of this class this morning, which is the impaction control is quite complicated, and for driving, one of the difficult part of driving is parallel parking, right? It's very difficult because parking space is very limited in busy city like in Ho Chi Minh City here. Parking is very difficult. Same as in Seoul, same as in New York City. So parallel parking is very challenging, right? So if you try to do the parallel parking, do you park it? It's easy to get out of it, right? But it's very difficult to get into. You have to try several times. And the space is very limited, right? So you have to go like this to make a parallel parking. So it's same as treating the impacted teeth. So the tooth is located very strange, weird place, and you wanted to put it in this place like parallel parking. It's very difficult to have it at one stage. We have to make it in several trials, right? Let's see how experts are doing parallel parking. This is what experts do in parallel parking. And I wonder if you have attended a course about treating impaction. Please raise your hand. Have you ever got the course attend a course about explaining the treatment of impaction? Or have you ever seen the case presentation on impacted tooth successfully? Many times, right? Many doctors are advocating that I'm doing very well in impaction treatment, right? The thing that I want to say is that even this expert is do the parallel parking like this. Well, he does much better than us. However, to take this video, I think he have tried it several times, right? Same is true in presenting of the impaction case. So do not get fooled by presentation. They only show you the success case. Okay? If you do every patient successfully with only one trial, he is an expert like this. But even the expert like this cannot succeed it in one time, single chance. So he have tried it several times, I think. So does the doctor who showed you the impaction treatment case. So please do not get fooled by it, okay? So he's only showing you the successful case, okay? And this morning I would like to let you know how we do it in one trial to do the parallel parking like this, okay? So what I want to say is that even if he did the parallel parking very nicely, what I want to say is the success rate. Suppose there are severely impacted teeth, and some doctor shows you very successfully treated case, and then what I want to ask him is that if there are 10 cases like that, and how many cases have you been successful? Success rate is very important, not at the single instance, right? So let's take a look at the case that I showed you at the beginning. Let's take a look at this case here. It's a surgical open case. I stole it from the internet. I don't know who's the owner of this picture, but I just stole it from the internet. So he made a surgical opening and put the bracket at the crown over here, and put the single force downwards here. And many of you, or he, may believe that if you apply the force at the crown is going to follow the force. He believes that way, right? So if you put the force over the crown, you might think that the crown moves downward like this, and treatment will be successful. But let's see. What I want you to do is take a photo of this screen here. Take a photo of this, okay? And save it to your computer and open it in central rotation calculator and confirm if this works. So I open up the central rotation calculator here, okay? I already saved it, so I'm going to open it. Import JSON. This is a surgical open case here. Now, as you can see, in the image it's cuspid, not the incisor, right? But my central rotation calculator is a incisor facing to the right side. So it might not be applicable, you might think. But the shape of the tooth is just artistic. It doesn't mean anything. It could be facing left or right, it can be either cuspid or incisor. So that's why I inserted the function of control 1 and 2. If you press control 1 and 2, only long axis will be displayed. And the shape of the incisor is not relevant. It's just artistic. Okay? The important thing is just long axis, not the shape of the tooth. Okay? So don't blame me that you are using incisor, not the cuspid, but it doesn't matter. Okay? You get the idea? The shape doesn't matter. So you can see the long axis is exactly same as this cuspid over here, right? So I'll leave the shape of the tooth like 1 or 2. Once again, it looks like incisor, but it's cuspid. Functionally, they are the same. It's just artistic. Now, the yellow one, is the one before the treatment. I move the yellow one over the image like that, and put the blue one down here. That's the objective or plan. I want to move it downward here. And you can see that the center of resistance to begin with is somewhere over here. And the center of resistance after the treatment is somewhere over here, right? That means center of resistance should be moved quite long distance, forward and downward, right? The trajectory of the center of resistance says the line of action. So if the center of resistance moves from here to there, the angulation is exactly same as the line of action. The angulation of the force should be exactly parallel with the trajectory path of the center of resistance. Then the next question is, we got the angle, but next question is, where would you put the force? It can move up and down parallelly. So that determines by A and B. So it says A is 3 millimeter, right? That means force should be applied 3 millimeter above the center of resistance. So this is the correct force should be applied here. So let's do the simulation. You see that? If the force should be applied like this. You see, trajectory of apex moves this way. Center of rotation, the center of resistance moves this way, and the apex moves this way. And this is the trajectory of center of rotation is moving slightly. Okay, and the correct force system is somewhere over there. So I start the simulation by clicking my signature again. So once again, you can see that the correct force system is somewhat like this. So that means force should be applied somewhere here, not here. You might think if you apply the force downwards, the crown will follow the force, but never follows the force. So let's simulate that kind of force system and what will happen. So I'll try to import again. I saved it already. This is what happens. I move the blue one arbitrarily somewhere else, not our plan, but instead I try to match the force exactly same as this operator tried to do. So if now you can see the line of action is like this over here, same as the one that he's applying. So if the force is applied like this, okay, rather than center of resistance moves forward, the center of resistance moves downward, parallel with the line of action, and crown moves backward like this. So if you put the bracket over here and put the force downward, it's going to move like this. And that's not what you want to move, right? So the center of rotation calculator lets you know how to design the force, if this is correct or wrong. So in this case, I would say, rather than saying wrong because it's not my case, it's not good, okay, I would say. Let's take another case. This is a case that I quote from the AJL. You can see that bracket was placed not at the crown. The bracket was placed at the cervix instead of the crown, right? And force was applied a little bit distantly. And my question is is it good or bad?
Cái này có tốt hay xấu anh chị?
We'll confirm using a calculator.
Và chúng ta hãy tính thử là theo cái tính toán này.
This is the
Đây là cái
before,
vector của lực nha. Mà cái
and
người
this is
bác sĩ
after.
của ca này trên tạp chí Chính nha Hoa Kỳ đó.
Now you
họ
can
tính
see that
mà các bạn sẽ
the planned force system exactly same as the line of action he applied.
dạ,
That means
điều đó có nghĩa là
he put the bracket at the correct position, and he put the force system in correct angle
và như vậy
to get this result.
và để có được cái kết quả
I don't
này,
know if he have used central rotating calculator or not, but fortunately it became correct. I think
dạ,
he
cho
hasn't.
nên
He does. I wonder he knows or not, but
và tôi không
he
biết
did
anh có
the
biết hay không,
correct.
nhưng mà khi đưa cái hình này á và nói rằng
So,
là tôi sẽ dùng
this
cái lực đó
case,
kéo vô đây là xạo.
Once again, bracket is put at correct place. So this is the point of the bracket, as you can see in the red dot
Và
here.
như vậy cây mắc
If
cài
the red dot in an infection control,
và trong kiểm
the
soát
red
cái
dot should be located at the line of action.
và chúng ta
That
có
means
thể là
the moment to force ratio should be always
lực
zero.
nó lên
If you
nó
take a
đi
look
qua
at here,
cái
you can
điểm
see
cho
that the
mắc
moment
cài
to force ratio is
và
almost
chúng ta
zero.
thấy cái tỷ lệ
Why is
trên
that?
lực á là
Most of the
ở đây
time,
hầu hết
when
các
you
trường hợp
do the traction of the impacted tooth,
khi chúng ta kéo một
you
cái răng
don't
bị
use
kẹt,
the wire.
chúng ta
You
không
use
dùng cái
only
dây,
the button or
chúng ta chỉ
bracket
dùng một cái
and
button
a ligature wire
và
or
một
elastic
cây
string,
sợi
right?
dây
Elastic
chỉ thép hoặc là
chain.
thun hoặc là
That
chuỗi
means
thun chuỗi
using
thì
an
chúng ta kéo
elastic
ra
chain without a wire,
và
that
chúng ta
means
sẽ
you
dùng
cannot apply
cây
the
thun
moment.
và không có cái dây
How
cung qua
much
cái
is
mắc
the
cài
moment to force ratio at the
và tỷ
bracket
lệ
in
lực
infection control?
và chúng ta nên có là để chúng ta có thể kiểm soát
Zero.
một cây răng đó
Right?
là cây
So whenever you put the
và bất
force,
kỳ khi nào
you
chúng ta đặt
cannot
cái
put
lực
the moment in infection
và
control.
chúng ta
So you always
chúng ta
have
đâu
to
có
put the
đặt được cái
bracket
moment.
at the line of action
Ví
so
dụ
that the
chúng
moment
ta
to
nhớ
force
rằng là
ratio
khi
is
chúng ta
always
kéo một
zero.
cái răng ra là chúng ta dùng cái lực đơn thôi, chúng ta
If
đâu có
you put
moment
the
được, chúng
bracket
ta đâu có
over
mắc cài,
here,
chỉ có mắc cài mới giúp
that's
cho chúng
supposed to
ta
be the
tạo
center
ra
of
được
the
cái
crown,
moment. Cho nên chúng ta phải tính
then
làm sao cho một cái lực
you
đơn
have
mà
to
nó
put the
lôi cái răng
moment.
đó ra.
You can see that the
các
moment
bạn
to
thấy.
force ratio becomes
Và
shows you some numbers. That means you have to apply the moment at the bracket. But if you are using a
Nếu
button,
như
you
á,
cannot
chúng
put
ta
the
dùng ở
moment.
đây
So
thì cái công thức
always
này để
you have
dùng
to
cho
put the
nó yêu
bracket
cầu là muốn
the
là
line of
cái
action
moment, nhưng mà trong tình huống thực tế trong cái răng
so
mắc kẹt
that
mà không
moment
có
to force
moment
ratio is
đó,
zero
chúng ta kéo
all the time, no exception.
chúng ta thấy á, là không có moment. Cái moment đó là cái moment của lực nó không qua tâm cả thôi, chứ chúng ta không có moment để phụ lực, không có moment của cực phụ. Mà cái moment ở trong cái công thức MGF là moment của couple các anh chị nha.
Now it's time to take a look at very weird
Và
case,
chúng ta hãy xem một ca rất là kỳ dị, một ca lạ lùng
very outside interesting case
mà cho chúng ta thấy là một cái ca này ca rất
of mine. It's my case.
đây là ca của tôi, đây là những ca rất là lạ lùng, rất là kỳ quái, rất là quái chiêu đó, quái rồi.
At the age of 8, he visited my office
Người bệnh
and I
nhân
took an X-ray. And what's wrong with this patient?
cái bệnh nhân này có cái gì sai?
What do you see
Các bạn
problem?
thấy được cái vấn đề là gì các anh chị? Các chị chẩn đoán thì đây là X-quang là có vấn đề gì? Các chị tương tác với thầy đi.
Spacing, yeah. Here, this.
Có cái vấn đề viêm quản không? Có người nói vấn đề viêm quản ha.
Permanent tooth is missing here, right? It looks like. And also, two lateral. These are central. These are centrals. These are laterals. There are two identical laterals. So I have to extract one of them. And they are look very normal. So I was very confused to which one to extract. Anyway, there's a supernumerary lateral here. And it looks like upper premolar is missing. But there's something strange over here. I don't see it yet, but let's take a look. So this is the patient at my initial visit, and I asked him, as we don't have a permanent teeth,
không
let's
có răng
wait,
vĩnh viễn.
and I'll see you next week.
Thì,
So 1 year will pass.
Yeah.
See you again.
Xin sẽ gặp lại.
So next year he visited me again, and you can see that there's a supernumerary tooth and some kind of strange structure is here. I don't know what it is, but
Tôi không biết tại sao nó lại lộ ra
the
cái này.
angulation is not good.
Không biết là không biết là lúc trước á, cái góc độ chụp
So
phim
I
đó.
asked him to wait, let's see next year. So 1 year is another year is going to pass. Next year, so I extract the lateral here
Thì lấy 10 tuổi
and did nothing.
từ chỗ cái răng hai mà nó dư đó. Thì bây giờ là đã có được răng ba, răng sợi bốn, răng năm thì nằm ngang. Rồi còn góc thì
And my message here is never try to pull it downwards. Just let it comes down once you open up the space. Okay? Let's just gravity will work. So next year I did nothing but to extract the one of the lateral. We kept waiting. So it comes down a little bit more and more. Still waiting. So I've been waiting for 5 years. Did nothing, just extract the lateral and let the cuspid move down. And you can see that this one over here is like this. And what did you do? As there's no space, I transferred this patient to the oral surgeon, consulted the oral surgeon to extract this. And the surgeon told me that it's too deep and the position is not good and the patient should undergo general anesthesia and it's very difficult and nobody wants to extract that. So I explained it to the parents. Nobody wants to extract. So I cannot extract, so let's just keep waiting. Unless there's a pathologic change like cystic change or something. So let's just let it go. So next year I started ortho treatment. So we have a missing above here, so lower cuspid was extracted and kept waiting. And it goes up like this. It goes like this. Maybe next year it's gonna pop out from the nostril. Goes up and up. Keep going up. 15 years it goes up.
10
Right behind the
18
nostril.
tháng nó lên nữa, nó
You
lên
can
nữa,
expect
đủ
it
hướng
to
nó chạy
here.
thẳng lên.
So treatment has been finished by
Điều trị chỉnh nha xong.
18-year-old. So
18 tuổi.
whole treatment kept like 10. This patient is 10-year follow-up.
Như vậy là toàn bộ thời
So
gian theo dõi là 10 năm.
what I want
10
to
năm.
tell you is that
Đúng
if
rồi.
you see the impaction,
Nếu các bạn gặp một cái răng mà mọc kẹt,
the traction of impacted tooth is not the only solution.
cái kéo ra không
So
phải là giải
as
pháp.
we are an orthodontist, if we see the impacted teeth, we
Chúng ta là bác sĩ
instinctively
chỉnh nha,
wanted
chúng
to
ta
pull it
có
down.
một cái bàn
But
nặng ra
sometimes
giống
just
như
leave it
đó.
alone is
Và
another
kéo
alternate
nó.
choice.
Cho nên chúng ta
So
nên nghĩ
what I want to
cái
say
cách khác.
is extraction is
Và chúng ta
not
thấy
cure for all.
và
So
cho nên chúng
sometimes
ta thấy
just let it go.
đôi khi
Leave
chúng ta
it.
cứ để nó ở đó hoặc là bỏ quên nó lo mà để cái răng nào mà nó nằm cố gắng không.
If you are to tract it, if you want to make an traction, where would you put the force?
Kéo nó ra.
So you can take a photo of this and open up the central rotation calculator, and it shows that if you want to move this one to here, extract this and move on to here, force should be applied somewhere here. And as you can see here, the bracket should be put it somewhere on the line of action I said, right? Is that possible here? No. You cannot put the bracket over the same line of action. So it's very difficult to pull it downwards using a simple bracket and single force. Now let's take a look at that. This is a case before and after, successfully treated. Still there is an impacted tooth somewhere here under the nostril. And this is a case that I showed you at the beginning of this lecture this morning. Here is the impacted incisor over here, right? So my question is, where would you put the force? And what is the direction you want to pull it? That is my question. If you take a closer look, here is the cortical plate, and I think it is not shown under the gingiva, but the incisor tip is poking out of the bone like this. I think the X-ray shows. So if I trace it, it goes like this. So the incisal edge is poking out of the plate. I think. I haven't opened it up, but I think it is like this. And this is my plan. I want to pull it downward something like this. And I made a plan using a center of rotation calculator and find out the shortest, most efficient location of the force using a center of rotation calculator. So let's try to see it. Once again, I saved it, so I'll open it. This is my plan. Here is the initial position, and this is the final position that I want to make it downward. Okay, so where would be the ideal position of the force? It is something like this. You can see here. So force should be applied like this. So let's take a simulation and see what happens here. So this was my plan. Is this plan good or bad? It's good. It's most efficient. There's no round tripping. It moves the shortest distance, minimum rotation, right? But take a look at the trajectory. These are the trajectories, right? These are how apex moves from here to there. The incisor moves from here to here, and this is a moving center of rotation. Now, take a closer look at the trajectory of the incisor over here. Incisor tip is poking out of the place to begin with, right? And it moves down, going through the plate, the cortical plate. It's sweeping down, and the enamel is sweeping down. In the backside of the enamel, there's no cementum, there's no osteoblast or something like that. So if the crown is sweeping down through the apical plate, the cortical plate, what will happen on the backside of here? So what I want to say is that it's going to reserve all the labial cortical plate, and there will be no new bone formation behind it, I think, right? So biomechanically, it seems like very efficient way and correct way to track the incisors downward. However, what happens is like this. This is during treatment. This was not my case. This is a patient after treatment. In the lateral cephalogram, it looks like successfully treated. But if we take a look at this is before, this is after. And this is what happened. So once again, as the enamel is sweeping down all the labial, it reserved all the labial cortical plate, and the behind the enamel there's no bone for new bone formation. So this kind of gingival recession is inevitable. So what I want to say is that biomechanically it's correct, but clinically it's not correct. So clinically, what would you do? We have to do it in 2 stages. So how do you do the 2-stage treatment? So we can use calculator. It's just an assumption. It is already finished case, and it is very easy to tell them what's right and wrong on the treated case, but it's just an assumption. If I were treated it again, I would do like this. It's just a scenario. So rather than moving apex directly downward like this, I'll stop simulation. This is the patient to begin with. And I have to make a plan in 2 stages. So I have to move the incisal tip inside. So rather than putting a straight one stage operation, I move it backwards like this. Moving something like this. This is the first stage that I have to do. As you can see here, so let's do the simulation. As you can see here, incisal tip is moving from here to there inside the bone. So where would you put the force? Is somewhere back here, not here. So force should be applied quite downward and backward, somewhere here, not somewhere here. Okay? So it might intrude the incisors, intrude the posteriors. So it might prevent open bite at the same time. If you apply the force over here, then it's going to move down, but adjacent anchored teeth is moving up. So open bite will be developed. So rather than having the force at the incisal region, if you apply the force backward here, incisal tip is going to move backwards and downward, and the molars are going to intrude a little bit. So let's see what happens. So let's do the simulation. As you can see, the tip is moving inside the bone, okay? And then move it downwards to the final position. Like this. So as you can see, this is the trajectory of the movement of the central resistance, and this is how incisal tip moves. It goes downward and backwards, and then approach the final destination in 2 paths, not from the direct linear pathway. This is the position of the center of rotation here in the first stage, and this is the center of rotation at the second stage. So, if this patient visited me again, I think I would extract it. Rather than doing, she has been undergoing this treatment for 5 years. He had been treated for 5 years, but my previous doctor did it for 5 years. And the final result was not satisfactory. You should anticipate there should be a gingival recession like that if you did it that way. So I would say my final word would be, in impacted tooth, traction is not the only solution. So sometimes you need it in 2 stages. Sometimes you have to leave it that way. Sometimes you extract it rather than pulling out. That is my message in this morning. Thank you very much. Okay, any question? Yes.
So in a canine traction case, we often just bond the gold chain on the palatal side and then check it onto the arch wire. You said that the canine would tip distally if we have pulled the force downward like this.
Yes.
But in real scenario, we can like change the direction of the pulling force in the midway in the traction, and then try to move the crown more mesial by applying a more mesial force. So, yeah, what's your thought on this? Like,
Yeah, that's exactly what I'm saying. If you did multiple stages of treatment, whether you know it or not, you did not move it at one stage, one phase. You did it multiple phases. You did it correctly. Yeah. The force direction is keep changing, right? But the path, if you track the passage, it's not a direct path. It's going to move around, a little bit round tripping. But clinically, that's much more acceptable. Good question.
And then second question is, I think that like if we bond the gold chain on the impedance tooth, we cannot apply couple, we cannot apply force.
Với cái dây chuyền vàng mình không có đặt được cục
And
bộ.
then if we want to try it in one go, then it's better for us to bond the gold chain on coincide with the line of force
Và chúng ta cần
application.
phải dán cái gold chain
As much as possible.
Yes,
đến phương của lực
but
thì
many
nó
of the
mới
time, the line of force application is like limited by the anatomical constraints.
do
We just
những cái
cannot bond
dây
it.
thủ
Like,
mình không có
for
dán
example,
được
if we have an ideal force that is very close to the apex of the
phải cố gắng làm sao cho
we
nó
can't bond
gần
it
cái
there. So how would you?
You do it multiple phases.
chúng ta phải
You
làm
have to
nhiều
do
giai
it
đoạn.
in multiple phases.
Cho nên cái chuyện
It depends on
cái lực nó
the
ra
case.
giai đoạn đó mà
Let's discuss
cái
about
phương
it
của lực
and
á,
send me
không
the
thể nào
case.
qua
Discuss
được
about
cái
it.
điểm mà gắn cái
But what I want to say is
tôi
that
muốn nói rằng chúng ta phải
having
chia ra
one phase is biomechanically most efficient way.
là một giai đoạn là một mặt
It
là hiệu
eliminates
quả về
downstream.
sinh cơ học.
So
Nhưng
as
mà
much
đôi khi
as
chúng ta không
possible,
làm
you can
được.
do it directly,
Chúng
right?
ta không có kỹ thuật, chúng ta thiết kế
That's
được
not always
nó.
possible,
Chúng ta tính
however.
ra được cái đó mà chúng ta không triển được.
And the third question is more theoretical.
Và cái
I
này
want
câu
to
hỏi này
just
nó
want
lý
to
thuyết hơn.
double check that A is the distance of the line of force application and the center of resistance.
Từ
I want to ask which center
cái
of
phương của lực đến
resistance.
cái
Is
tâm
it the
cả.
before or is it the after?
It doesn't matter. It's a
Cái này là
perpendicular
A đến
distance.
B đó là trước.
So center of resistance moves in linear direction, right?
Oh, okay.
So it's a perpendicular distance.
So the line connecting the before and after, connecting the center of resistance of the truth position before and after, was the perpendicular force.
Well, it's keep changing. So if you do the simulation, you can see that instantly it's
Và
always
các chị thấy á,
you
là
can
từ
always
á,
get the exact
cái vị
distance.
trí ban đầu
It's keep changing.
nó thay đổi liên tục.
And then B is the distance between center of resistance and center of rotation.
Right.
And which center of
B á,
resistance
là từ tâm
again connecting.
It's keep changing. If you do the simulation, center of resistance keep changing. Okay, so these are all measure the distance from here.
thì nó như vậy.
Then clinically, what's the use of knowing the A and B?
That determines where you put the force to give a zero rotation.
Và tùy theo
So
cái
if
chúng
you
ta làm
design
như
the
thế nào
position, okay,
và chúng ta sẽ thiết kế.
from before and after, okay, then center of rotation is determined right after you reposition the tooth.
Yeah.
Then the solution will give you where you put the force.
Và
It gives
tùy
you the
theo là
number
chúng ta
A.
đặt cái lực ở đâu
That's
cho
the
nên nó
distance
đổi
where
cái
you have to
A
put the force
đổi
and the
cái A
angulation
thì nó sẽ đổi cái B.
clinically.
Dạ,
Right?
trên lâm sàng là như
I
vậy.
showed you that in retraction case,
Dạ, trong trường hợp chúng ta
to have the retraction and intrusion,
và
So
chúng ta
the force is
lưu ý
applied at the cuspid region, cuspid bracket area,
và chúng ta
and
thấy
45-degree upward and backwards,
và thường thường nó
and
tầm
it gives you
45
the
độ.
exact central rotation that
Và
we
như
play.
vậy á, thì chúng ta thấy trong cái tình huống mà chúng ta hay gặp là lui lên người là 45 độ. Cho xin một cái micro, nếu như mà ở Việt Nam muốn hỏi câu hỏi thầy thì tôi nói như micro là ở giáo viên Việt Nam muốn đặt câu hỏi
Okay,
thì
we'll
cứ
see
hỏi.
you after the lunch.
Thôi thầy nói là kết thúc